Section 2.8 talks about subspaces of Rn. That's very important section. We need to really get a solid understanding on this. So what a subspace is any set in the same space that has three properties. The zero vector is in it. If you pick two vectors in it and you sum them, they should remain in it. And if you pick a vector in H, this set, and you multiply it by any scalar, it should remain in H. So basically this is closed under addition and scalar multiplication. Not multiplication. So, the first two problems are visual. We're going to look at those, but it says display sets in R2, that's X and Y, R2, R3, X, Y, and Z. Assume the set include the bounding line. In each case, give a specific reason why the set is not a subspace. Okay, what does that mean? Well, a couple of things you could do. You could take, for example, two, not numbers, vectors. So one way of doing this, again, you could do this so many different ways. You could say, take U to be 2, 0. And take V, let me think. Take U to be 2, 0, that's enough. If I take -2 times U, that would be -4, 0. -4, 0 is not in the set. So, kind of just mimicking, this is set H. It's all of this shaded part. So this doesn't belong to H. Therefore, not a subspace. You don't have to show all three conditions don't meet. You could just say it doesn't satisfy the scalar multiplication. So there are many ways you could do this. I mean, you could have picked another. You could have picked 1, 1, multiply it by -1. It would be -1, 1. That wouldn't work. You could say on number 4, let's do addition. You could say this is vector 2, 0. And this is vector 0, -1. So this is, call this U, call this vector V. If I take U plus V, I will get 2, 0 plus 0, -1, which is 0, -1. And 0, which is 2, -1. 2, -1 is definitely not an H. H is right there, right? So again, if you say no, you just have to show a counter example, and that's good enough. You don't have to say much. Those are not official proofs. Those are more like a show. An official proof, you have to start with a general case. Let U equal A, 0, A is bigger than 0, 0, B, B is negative, you add them. But we're just going to do examples. We're applying this by example more than, it's a lot nicer that way. How about this problem? Given three vectors, 1, 2, 3, and a fourth vector. Determine if U is a subspace of R4 generated by those three vectors. So those three vectors generate this R4 because 1, 2, 3, 4. Okay, 4, that's fine. They're asking, is U a subspace in there? Well, the easiest way to show that is really to change the question and ask, is x1 v1 plus x2 v2? Okay, I'm getting excited there. Plus x3 v3 equal U. Basically, they're asking, again, we come back to the same thing over and over. algebraically, that's how things are going to work. 1, negative 2, 4, 3. 4, negative 7, 9, 7. 5, negative 8, 6, 5. And does it equal? Basically, I'm trying to see if this has a solution. If it has a solution, then this is a linear combination of those. That would mean it is a subspace. And if it's not in there, and if I do the work and get it into echelon form, what do you notice? Contradiction, no solution. So basically, that's how we're going to check if a vector is a subspace of a matrix. This is matrix A. No solution. Oh, why did I put a comma there? No solution. Oh boy. Therefore, U is not a subspace of V1, V2, V3. Alright, another definition says column space. The column space of matrix A, we denote that by column of A, is the set of all linear combinations of the columns of A. Alright, again, they're giving us A right there. They say A is this combination. These are the columns of A. Determine if P is in the column of A. What again? Linear combination. They're asking, does AX equal P? Or does X1 V1 plus X2 V2 plus X sub 3 V sub 3 equal P? Well, the same deal again. If I put this in and I list negative 306, negative 223, and 0, negative 63, and see if I get a solution out of this. And if I do the magic again, so here, I get an infinite amount of solutions, which means it's a consistent system. And if it's consistent, then there is a solution, yes. P is in the column of A. And that's how it works. Now, a very important definition. Extremely important. We're going to leave that for a while and come back to it heavily later on. Null space is a massive deal in applications. So, a null space of a matrix A, and we set it as null of A, is the set of all solutions of this equation. You take AX, you set it equal to 0, and you solve it. Another way of saying that, the null space of an M by N matrix is a subspace of Rn. It's in the range. Equivalently, the set of all solutions of this, of M homogeneous linear equations in N unknowns. Not saying much, just restating this. I was going to skip that, but I thought I'll put it in just in case. If I look at this problem, number 10, it says, did I give you a page number? Yeah, 153. So if I look at number 10 and I notice it says, with U equaling negative 2, 3, 1, and A as an exercise 8. A as an exercise 8. So there it is. There's A. A is negative 3. Those three vectors. And did I get them right? Yeah, I got them right. Okay. They're asking, determine if U is in the null of A. So what does this mean? What again is the null of A? That's confusing. AX equal B. There's A. There's U. They're asking, is it in the null? They're asking, does AU equal 0? That's all there is to it. Well, what's A? A is actually negative 3, negative 2, 0, 0, 2, negative 6, 6, 3, 3, multiplied by negative 2, 3, 1. So that's what the null is, mapping everything to 0. And if you recall, we could do this many ways. I'm going to do this as a shortcut. That generates the first row, that generates the second row, that generates the third row, and in order, negative 3 times negative 2 is a 6, minus 6 plus 0, that is 0. That's not enough. 0 plus 6 minus 6, that's also 0. And 6 times 2 is negative 12. 3 times 3 is a 9. And 3 times 1 is a 3, and that's a 0. So yes, U is in then. And do you see how I'm always writing those answers? So that on the exam there's no discrepancy. Oh, I did mean, I didn't. You write it out. You don't assume I know anything. I know everything, but you assume I don't know anything. Okay, 14 says, for A as an exercise 12, I already copied. This is from exercise 12. Find a non-zero vector in the null of A. A non-zero vector in column of A. Okay, what does that mean? Null of 0 and column of A. Well, null of 0 means what? Null means AX equals 0. They only gave us A. So what does that mean? That means we want to take this A, we want to multiply it by x1, x2, x3, and get it to be 0, 0, 0. And we know where this is going, right? The usual. The part that's never going to leave you alone. I forgot one of them. Oh, no, 3 of them. This is a 4 by 3. This is a 3 by 1. And the outcome is a 4 by 1. There we go. Much better. Okay, now again, I'm going to do that magic trick. So if I work this out, that's what I'll get. That's 5/3, and that's negative 1/3. So doesn't this mean that, and again, to really figure this out, right? x1, x2, x3. There are 3 of them, right? So I know that x3 is 3, and x2 is negative 5/3 x3, and x1 is 1/3 x3. So basically, x3 times 1, negative 5/3, and 1/3. Any multiple of that will do. This is the null space. For the column space, you all need, for the column vector, you just need a non-zero. Let x3 equal any non-zero. The book doesn't like fractions. They normally choose multiples of 3. So you're looking at 3, negative 5, and 1. Any multiple of that will do, but here they want specifically a non-zero vector. Normally this is the answer, but here that will be one non-zero answer. And this way you could hit 2 birds with 1 stone, which is really bad because you shouldn't hit birds, but you know, the metaphor. Oops, okay, that didn't work. Let's talk about bases. This is an introduction to bases, slightly different idea. Bases are a bit different. A basis for a subspace H is a linearly independent set H that spans H. So for 1 dimension, we use 1. For 2 dimensions, we use 1, 0, 0, 1. For 3 dimension, we use 1, 0, 0, 0, 1, 0, and 0, 0, 1. Those are the traditional. Basically, all what you do on 1 dimension, any multiple of 1, you can't choose 0 because then you're stuck with 0. But 1, any multiple of 1 will do. if you go to 2 dimensions, then if you take the vector 1, 0, and 0, 1, that represents any point on the 2-dimensional space you can get. And if you go for 3 dimensions, to pinpoint any location, you need any multiple of 1, 2, 3. 4 dimensions, you add a 0, and so on and so forth. 0, 0, 0, 1. Okay, you multiply those. And let's talk about what it means to be bases. Bases is a big deal. This is an introduction. The pivot columns of matrix A form a basis for the column space of A. Okay, we want those to be linearly independent. We know what that means. Be careful. This is a warning. The pivot columns of A itself form a basis for the column of A. Do not use the reduced. It has to be the original. So they're asking, determine which set in 15 through 20 are bases for R2 or R3. What does bases mean? Those two, are they linearly independent? There are a couple of ways we could figure that out, right? Since there's only 2 of them, it's very simple. If I call this vector U and I call this vector V, do you see that if I take 2 times V, wouldn't that be U? So those are linearly dependent, right? Therefore, they do not form, they are not bases for R2. Next problem is asking again, determine if these sets form bases. You could write this as 1, 1, you're trying to see if these are multiples of each other. So one way of doing this is to set it equal 0 and see if that works. And again, there's another way I'm going to show you really quick. I'm going to copy something. This indicates that the only solution is x3 is 0, x2 is 0, and x1 is 0. So yes, they are linearly independent. Another way of doing this is to look for the pivots. 1, 2, 3, and they're talking about R3, so yes, it works. Those are linearly independent. They form bases because there are 3 of them. When I get to this problem, now a couple of pointers about it. The same deal, I could look at it and say, well, I don't have to do it, but let's say I didn't pay attention to that. Then you're going to do a lot of work. Do you see what's wrong with this? Do you see that the weights are 4 of them? That means one of those is already the 0. That means you have an infinite amount of solutions. That, yes, forms bases for R3. So those are linearly dependent, no. Or you could start by saying, look, if I have 4 vectors, for them to be linearly independent, I need 4 pivots, but I can only get 3 at most. There's no way of getting a pivot out of that. That'll be a lot more efficient. I'm going to show you the reduced. Actually, I'm not. There are more vectors than entries. Well, that means one of those has to be multiple of those 3. So no, they do not form bases. Okay, I meant for those theorems to be here, not up there. I made a mistake. I'm sorry. So here, this is the theorem. It says the pivot columns of a matrix form basis for the column space. Be careful. The pivot columns of A itself form basis for A, not in the reduced. It has to be in A. And here they worked out the problem. Again, they want to make sure that you're getting this. They're asking about 2 things. Display a matrix A and echelon form of A. So they did row reduction. Find the basis for the column of A. Look at the pivots. So, this vector and this vector, doesn't this correspond to this? So you say the column of A would be negative 3, 2, 3, and this corresponds to this. Again, the original, there's a warning in the book, they explain that by modifying those, sometimes they don't match the space anymore. That's done. And then they ask about something else. Find a basis for the column. This is basis for the column, which means those two are multiples of those. Basis for the null. What's this null business? Extremely important. Set AX equal to 0, or set negative 3, 2, 3, 9, negative 6, negative 9, negative 2, 4, negative 2, negative 7, 8, 2, 0, 0, 0, and solve. And I'm gonna get this as well. And if I solve this, so again, the pivots are right here, and they're extremely important. They tell you that's x1, x2, x3, and x4. So that tells you out of there automatically that x4 is free. x2 is also free. x1 is 3x2 minus half of x4, and x3 is negative 5/4 x4. So if I really write this, let me see if I need that. Actually, I could back up a bit. I could say this is actually, let's see. So that is if I separate those, x2 and x4. x2 times 3, 1, 0, and 0. And x4 times negative 1/2, 0, negative 5/4, and 1. So basically, if you want the bases, will be any multiple of 3, 1, 0, 0, and negative 1/2, 0, negative 5/4, 1. I do need to warn you, any multiple of those will do. So don't be surprised to see that as negative 2, 0, negative 5, and a 4. They multiply this by 4 to clear the fractions. You don't have to. This is basis for null space. A massive deal for us that's coming up. Same deal on 26. They give us A and they tell us how this works. Well, let's see. Pivots. x1, x2, x3, x4, x5. So the bases for column of A bases for column of A would be the original 3, negative 2, negative 5, negative 2. Second, negative 1, 2, 9, and 6. And 3, 7, 3, and 3. Something we're not making connections for to yet, and we don't have to. And figure out the basis for the null space. We want AX equals 0. So we're basically going to take this 3, negative 2, negative 5, negative 2, 1, 2, 9, and 6, 7, negative 2, 3, and 6, 3, 7, 3, and 3, 954 and 7 0 0 0 0. Now I do have a trick for you. You could start automatically with this. If they gave us that, no need to start from the very beginning. Just continue where they left off. It's very easy to pick this up at this stage. And reduce that even further. And what you will get will be, and reduced, it's right there. Again, you'll notice. Do you notice? The pivots don't change. And now what? Now, x sub 3 is free. That means all my answers will be in terms of that, and x sub 5 is free. So, let's start. Let's start from the bottom up. If I'm looking at these equations, I notice that the top down, x sub 1 is negative 3x sub 3 minus 5 halves x sub 4. X sub 2 is I didn't line them up properly. Negative 2x3 minus 3 halves x4. x3 is x3, that's free. x4 is negative x sub 5. So if I really write them out, you don't have to do this, but I'm gonna write them out step by step in case you were confused on the previous problem. You want to separate those. That's what they call biparametric equations. You want to separate those into x3 times what? And x5 times what? And those are the two vectors that will form basis for the null space. There's a negative 3, there's a negative 2, there's a 1, a 0, and a 0. There is a negative 5 halves. There is a negative 3 halves. There is a 0. Something's not right. This should have been x5. Negative 1 and 1. So if I want the bases, again, you could jump from this to this straight. Bases for null space. Again, a massive deal. You'll see it the last thing we do in this class using differential equations. Basis for null space would be the negative 3, negative 2, 1, 0, 0. The negative 5 halves, negative 3 halves, 0, negative 1. Any multiple of those will do. And there's our homework. I give you a section because there's some work to be done. Not a whole bunch, but there it is.